Good day, everybody. Welcome back to another video from the Mathnasium. Today we're going to start our unit on solving systems of equations. In this unit, you're going to be learning three methods for solving system of equations, and today is the first method. But first, I want to go over what this game is, what it had to do with the time period in which it was produced, and how does that pertain to solving a system of equations. So the game you see in front of you is called Missile Command. I believe it came out in the 80s. And in the 80s, there was a lot going on this topic of missiles, and that's because it was kind of the end of the Cold War was wrapped up in the early 90s, and Ronald Reagan and Gorby were basically were pulling missiles out of Soviet Union, and I'm not a history buff by any means, but missiles were a hot topic. Everyone was worried about missiles coming, to the United States, yada yada yada. So that it makes sense that this game was produced then. In Missile Command, you are basically operating these three missile towers, and you're firing interceptor missiles to try and basically blow up the missiles that are coming in to hit these towns, but you want to blow them up in the air so they don't hit the town. So that's the whole point of the game. So how is this relevant to us here in Alaska? Well, here in Alaska, we just happen to have one of these little stations right here. Fort Greely is one of the it's really close to Fairbanks, is one of the United States missile defense stations, and they might fire an interceptor missile if something was headed over the North Pole, headed for the United States, or headed for us. So they would fire an interceptor missile. So what does that have to do with solving systems of equations? Well, in systems of equations, all a system of equation is you basically have two lines that are on a coordinate plane. And they represent really kind of two things that are being measured, or two different situations in the real world. And the solution to a system of equations is the point at which those two lines cross in the coordinate plane. Okay, so the solution would be right here where they cross. Well, it turns out, although this is an oversimplification, that's basically what's happening if a missile is being fired at the United States. So, this is the timeline of events. A missile, and I'm not an expert at this, but the basic idea, I guess, would be if a missile is being fired at the U.S., we'd be collecting information about that missile and hopefully trying to figure out a spot where we would like to hit it. So we're looking at kind of what is the path of the missile coming at the United States look like? What is the hypothetical missile? It's not actually happening. What is the path of our interceptor missile that we're going to fire, and where are those two going to meet? The math there is much more complicated, but you want the person making those decisions or programming the programs that help guide those missiles to have a solid understanding of systems of equations and getting things to come together and meet together based on the data that has been collected or the information that we know. Okay, cool. So yeah, we're going to get to that in just a second here. Okay, so like I said, the solution, if you have two equations, you're going to be graphing two equations and finding the point where they cross. The solution to a system of equations is the point where those two lines cross. Well, it turns out that there are several situations that there's several ways for two lines to interact. It turns out lines don't always cross. So what I'm going to go over is what are the three possible ways that, or three possible situations two lines can interact in a coordinate plane. Okay, the first is if those two lines have one solution. So I'm gonna just, if you would here, just draw out a coordinate plane really fast. I'm gonna group these together and copy and paste. So I'll make a quick coordinate plane, grab my pen, make sure I've got the black one selected. draw a little picture for each one. Okay, so situation 1 is a situation where the two lines cross at a point. So if two lines are graphed in a coordinate plane, okay, and they cross, the solution to our system of equations is a point. It is the point right here where they cross. It is the point that lies on both lines. That is the solution to our system. So what has to be true? There's one thing that has to be true for those two lines to cross. The thing that has to be true is that the lines must have, why is this in green? I used to switch to green. I'm going to switch back to red. The lines must have different slopes. Okay? In order for two lines to have one solution, in order for them to cross only at one point, they must have different slopes. So as long, if and only if, right? If they have different slopes, then there's going to be one solution. And if there's one solution, the lines must have different slopes. That has to be true. Okay? But that's not the only way that they can interact, right? Even if the slopes are just slightly different, so I got my pencils here, if the slopes are just off by just a little bit, eventually those two are going to intersect, even if it's not on our 10 by 10 coordinate plane that we always graph. If they are headed towards each other in any capacity, they're going to eventually intersect, cross. Okay, it is possible, however, for two lines to not ever cross. And the way that would happen is if the two lines have exactly the same slope. So let's go ahead and draw that scenario. And I'm just making up the lines, like these are not special or particular by any means. Okay, so the second situation is if you have two lines that are exactly the same slope. Okay, if they have the same slope like this, they're never going to cross. Every time this goes down 1 over 4, this one's going to go down 1 over 4. They will never ever touch if you go forever in either direction. So they have to have the same slope for this to happen, but it's also true that the two lines have to have, I'm going to save some time. They must have the same slope for this to be true. But it's also true that they must have different y-intercepts. If you're talking about this in the form y equals mx plus b, these two lines are going to have the same slope and different y-intercepts. So if you see that when you're looking at two equations, you say, oh, they both have slope 2, and they have different y-intercepts, I know that that's no solution. If they have different slopes, it's going to be one solution. And the last situation is the situation in which they have the two lines have the same slope, and they have the same y-intercept. Okay, same slope, same y-intercept. Let me see the screen. So basically, if they have the same slope and the same y-intercept, they are the same line, okay? So at how many places do these cross? Remember, because I said the solution to a system of equations is any point that's in common between the two equations. Here, they only have 1 point in common, so there's one solution. Here, every point is in common, so there are an infinite number of solutions. So that means the 3 ways that two lines can interact in the coordinate plane are if they cross once, if they never cross at all, and if they cross everywhere. So that'd be 1 solution, 0 solutions, or an infinite number of solutions. Okay, let's do some graphing, shall we? Let's find the solution to this systems of equations. So let's take a look. How many solutions will this have? Right off the bat, I can look at this and tell you how many solutions it's going to have. It must fall into one of these three categories. Different slopes, same slope, different y-intercept, or same slope, same y-intercept. So if we take a look back, these two lines have different slopes, so I know it's going to have one solution. So let's go through in red. Our slope here, identify M and B. Our slope is 1. Nothing's written there. And our y-intercept is 2. And let's go ahead and graph that line. Y-intercept of 2. We go right here, slope of 1. 1 as a fraction can be 1 over 1 or 2 over 2, yada, yada, yada. Up 1 over 1, up 2 over 2. I can all sorts of different ways to write it. Whatever. Okay. That's what our line in red looks like. And don't forget to put all the points on the line. So we got to connect those like so. Okay. Okay, in blue, let's identify M and B. M is -2, B is 2. Okay, so our y-intercept 2. Oh, they have the same y-intercept. Okay, so when I plot the rest of my points, slope of -2 down 2 over 1, we're going to see here what we have just found the solution to our system of equations. Sorry, I'm freehanding these. Got it. We just found the solution to our system of equations. The solution. Now, when you're showing your work, you need to graph your lines. You also need to state explicitly what that solution is. It is the point 0, 2. That is our solution. This is the point that is in common between these two lines. Let's take a look at this next one. All right, y equals 1. So go through, let's do the red one first, and give that a shot. So M equals B equals. Okay, M, the slope is always the coefficient of the x term. There is no x term, so that means the slope is 0. Our y-intercept is 1, so this has y-intercept 1 and slope 0. Slope 0 is a horizontal line, or you can think of 0 as a fraction is up 0 over 1, right? So this is what my line looks like. It's just a horizontal line at y equals 1. This can also be described as all the points with the y value 1. This is all the points with the y value 1. It's like a puzzle. Okay, so this next one. Okay, next one. And what the hoogie? What's going on? Let's try that again. M equals 1. Our y-intercept is, we're not adding any constant here, so the y-intercept is 0. So it must cross there. And it's got a slope of 1, which, as we said before, is up 1 over 1 all the way across our graph. We graph these, and we found our solution. So even though we found it, I want you to continue graphing. I'd like you to display the graph in all of its entirety. Okay, so our solution here is the point 1, 1. That is our solution. Now you could solve this problem verbally. These are the restrictions for our solution. The solution says, all right, we need a point. The solution is the point that has the y value 1, but we also know that its y value is equal to its x value. All right, so if its y value is equal to its x value and it has the y value 1, that means the x value must be 1. Done. Okay. Here's graphically how we found that. Okay, you guys try this on your own. How many solutions will it have? Pause the video. Answer that question. Also try and solve it on your own. Hope you could see that last one. Oh, that was a little funky. That's okay. I'm going to skip down, extend the page, so make sure we can see. All right, so hopefully you guys pause the video because I'm about to get going. Red line, here we go. Y-intercept is 1, starting at 1, it's got a slope of negative 1/3. Okay, that means it needs to be going downhill as I go from left to right. So coming down 1, if I go down 1, I'm going to the right 3. Okay, so we got our first line. Oh man, that's pretty. Ah, that is so hard to do. The angle I'm drawing. Okay. All right, there's line number 1. Line number 2, y-intercept of negative 3, slope of 1/3, up 1, to the right 3. Ooh, there we go. We found her. If you're struggling with the graphing portion, you need to go back and maybe watch the 2-2 graphing video. That might be helpful. So our solution here is 1, 2, 3, 4, 5, 6, negative 1. Woohoo! Got her done. Okay, sometimes, and on some of the questions, you're going to be given you'll be given a set of equations that are not in slope-intercept form. So how do we approach a problem like this? Well, in this class, I gave you 2 different methods for dealing with this. The first method is method 1. This is from 2-3. That's why I taught it to you. Is what I called forcing slope-intercept form. So to graph something that looks like this, you can force slope-intercept form, which means you solve for y. So to solve for y, first I need to get the term with y in it by itself. So I'm going to move the x term, or subtract 3x from both sides. That goes to 0, and you'll be left with 4y equals negative 3x plus 12. Okay, I am then going to get y by itself, I'm multiplying by 4, so I'm going to divide both sides by 4. Four divided by 4 is 1y equals negative 3/4 x. 12 divided by 4 is plus 3. All right, we got the red one. Y-intercept of 3, slope of negative 3/4, down 3/4, down 3/4. I had to go off my graph a little bit, and that's okay. And then up 3, back 4, double check. My slope was negative, so it should be going downhill. Yep. All right, and now we can graph this line. Oh, that was a little rough. Finding this. Don't think that was any better. You know what? I'm folding. I don't have a straight edge. I'm using the line tool. Ah, that's nice. Okay. All right, there's line number 1. Now the other method that I gave you, for graphing these, method 2 is plugging in points. So you can just pick an x value or a y value, and it'll give you the other one, and you can just plot the points. So if you picked x and you solve, it'll give you the y value, and you have a point that you can plot. And I said the easiest numbers to choose are like x equals 0. X equals 0 is the y-intercept, right? So if we plug in x equals 0 here, you're going to get 2 times 0. Let's not even write that term, which is just 4y minus 8. So that's y equals 2. So you get the point 0, 2. It turns out 0, 2 is not shared with the other line, but that's okay. And then I also recommended plugging in y equals 0, the x-intercept. So there you can just, this term's going to go to 0, and you'll just be left with 2x equals 8. Divide both sides by 2, and you'll get x equals 4. Aha, that's the point 4, 0. X goes in the X slot, Y goes in the Y slot. Hey, look at that. It's already on our graph. We can plot the rest of the points on our line. We know that the pattern is down 2 over 4, so I'm going to go down 2 over 4 again. We'll go up 2, left 4 like so. Okay, there we go. And now we have our solution. Our solution is the point at which the two lines cross, which is right there, 4, 0. Okay, now keep in mind, remember, if the two lines are parallel and they don't cross, then, so if they have the exact same slope, they're never going to cross. So there is no solution, so you should write no solution. If they're the same line, then you should write infinite solutions. There are infinite number of points. It is also quite possible that on some of your graphs, you will not get exact answers. You're going to get stuff that looks like this. Okay, if that's the case, you just estimate. So if I trace this up here, looks like it's maybe like 3.6 on the x-axis, and trace this over, looks like about negative 2.5 on the y. So it's okay to estimate. It still gives us an idea of the solution to the system, even if it doesn't fall on a perfect grid line. Okay, and the last comment that I want to make, and we kind of went over this before, a solution of a system of equations is any point in common between all linear equations present. You can have you can have more than 2 equations, but you won't see any in this class. And there's a way to algebraically check your answer, to check to see if your solution is correct. So you can check, is 1, 5 a solution to this system? Well, you plug those in, right? 1, 5, I'll plug in, we're asking the question, is negative 1, right? Is negative 1 plus 5 equal to 4? We asked that question. Well, of course it is. 5 minus 1 is 4. Great. Now I'm going to plug in down here. Plugging in 1 for x. This is asking the question, is 1 equal to negative 1? No, it's not. So this point is on the first line, but it is not on the second line. And since it's not in common between both of the lines, it's not a solution to the system of equations. Let's check over here. Okay, y equals 5. So I'm going to take from my point. My point has the y value 5. So that is on this line. It's that horizontal line at 5, so yes it is. And then this one down here, plug in 1 for x, plug in 6 for y. We're asking the question, is 1 equal to 6 minus 5? And the answer is yes. So this point is a solution to our system of equations. So what would that look like? That in slope-intercept form would be y minus x plus 6. So this is going to look like we have a line at y equals 5, and then plus 6. Oh yeah, so it looks like that. So that's the other line, negative 1. So that's where our solution is, 1, 5. Makes sense. Okay, cool. My last quick comment that I'd like to make is for those that are struggling with some of the strange lines that are on that assignment. There are some multiple that I think people are going to have questions about, so I'm just going to go ahead and go over that really fast. Remember, if you have something like I just went over, like y equals 3. If you want to graph y equals 3, that has y-intercept 3 and slope 0. Another way to think about this line, though, is it's describing a set of points. It's describing all the points with the y value 3. Well, how many points have the y value 3? This one does, this one does, this one does. There are an infinite number of them, and they're all on that line. So you can put a couple and call that good. Okay, and connect them with a straight line. how do you graph something that looks like x equals -4? Well, this also describes a set of points. It's the set of points that has the x value -4. So that's this point has the x value -4, this point has the x value -4, this point has the x value -4, so on and so forth. So this line is right here, all the points with the x value -4. So if you ever see anything that says x equals, it's a vertical line. If you ever see anything that says y equals, that's a horizontal line, and the solution to our system of equations is going to be -4, 3. Thanks for tuning into the video today. I hope that was helpful, and stay tuned for a few more on solving systems of equations. We'll see you guys later.